from video 1, where we looked at the starter, you will be able to now think about whether something converges or not. So this question here starts by asking for the recurrence relation, and it's the same one that we had in the starter. So we're just going to look at this one again, explain how we know it converges. So we are working with part A. We want to explain how we know it converges. Well, it's that value in front of un. There's a fancy term for the thing, a number that comes in front of a term. It's a coefficient. So as the coefficient, that's just a number in front of un, coefficient of un is between -1 and 1, then the sequence converges. So that's the first thing. We know it converges from that fact that if this value in front of the un is between -1 and 1, it converges. Now we saw on our Excel sheet by calculating loads and loads of values that it was getting closer and closer and closer to 30. That number it gets closer and closer and closer to is called the limit. And here we're asked to find the limit of its convergence. Now, at the limit, essentially what happens is terms get closer and closer and closer until they become basically the same term each time. So at the limit, the next term is the same as the previous term because they've got so close together that they are now the same thing. And we can use that to our advantage to find the limit. We use the capital letter L to stand for limit. So the next term, we put an L in. And the previous term, we put an L in because they have now become the same value. That's what we're saying happens at the limit. Great. And now we can solve that because we've got a little equation in L. Solving that, we take 0.5 L off both sides. And then we divide by 0.5. 15 divided by 0.5 is 30. So our limit would appear to be 30, which confirms what we saw with the Excel sheet. All our terms were getting closer and closer and closer to 30. And this little trick is a really neat way to find that. Now, let's have a look at a second example of this. So here we're asked to find the recurrence relation, the limit of the recurrence relation, which is this one here. We're going to use the same trick. Our next term being the same as our previous term is the little trick we're going to use. Let's take 0.1L off both sides. That leaves us with 0.9L equals -63. And then dividing both sides by 0.9, we get -70. So if I calculate the terms of this sequence here, we'll go towards -70. Now, there is one thing I would point out, and this is super important. At no point do we involve A0. And that means that it doesn't matter where we start, whatever number we start with in our sequence will always end up converging to -70. It might take longer or shorter amount of time, but it'll always get towards -70. The other thing I would point out, there is a little check you can do at the end here. If un equals -70, then un plus 1 equals 0.1 times -70. Sorry, not plus, -63. Check that. 0.1 times -70 is -7. Take away 63 is -70. So it does what we wanted it to do. The next term is the same as the previous one when we put -70 in. Okay, example 3, and this is kind of a non-example for a reason that's about to become very obvious. Find the limit, if it exists, of the recurrence relation bn plus 1 equals 4bn minus 12. This is a major alarm bell. So number in front of our bn, our previous term, is bigger than 1. That means the recurrence relation does not converge. So be careful. We need to check, always check that value. And technical term for that in this case is diverges. Okay, there's a reason I've written does not converge. Could jump up and down between two values or get into a cycle, but diverges is a good word. Now, I warn you, because if you have L equals 4L minus 12, you can solve that. You get minus 3L equals minus 12, L equals 4. This all doesn't fail even when that value is bigger than 1. But this is not a limit. If I start with 5 in here and put it in, that would give me 20, take away 12, which is 8. Put that back in, I get 32, take away 12, which is 20. Put that back in, I get 80, take away 12, which is 68, etc. The numbers will get bigger. This thing is not converging, even though this bit of maths here works. This bit of maths here is actually telling us about something you don't technically need to know about, called the stationary value of the recurrence relation, or an equilibrium value. So if I put 4 in, I will get 4 out and we'll get stuck at 4. But for any other value, any other starting value that I could possibly put in, this recurrence relation will get bigger and bigger and bigger, or smaller and smaller and smaller if you put negatives in to start with. So be wary. This works, but it is not a limit. And this bit up here is the key check to do before you start on any question. Now, one to do for yourself. Have a go, pause the video, and I will run through the answer in a second. We're good to go because that number there is less than 1. So it does converge, but can you find the limit? Pause the video. I'll run through the answer in a moment. Okay, let's have a quick look at the answer to this one. So the limit exists, and let's find it. Okay, so we're putting in L for our previous term and our next term. Let's solve that. So we get 0.75 L equals minus 15. Be careful with your negatives, don't lose them. Divide both sides by 0.75. So that is minus 20. And that is our limit for our sequence. So hopefully you got that, and you can get on with the examples now.